Looking okay? Okay. So my name is Rafael Gómez-Bombarelli, RGB, so I fully identify with it. I also work on photo switches, so I fully identify with the talk earlier. I'm an associate professor in material science and engineering, and my group works sort of on this arena of computational design of molecules and materials. And I think some of the themes are going to start sounding a little bit similar. Sort of the scope of why we want to innovate in chemistry and materials has to do with sustainability mostly, right? There is this pressing need to come up with more sustainable alternatives to materials that we use today, or to come up with altogether new materials that do jobs that we haven't asked of materials before, right? We need way bigger capability in energy storage, solar, maybe we need different fuels instead of gasoline and as an energy carrier. We need to figure out what to do with sort of agtech. And so there's this big problem in circularity, right? Recyclable textiles, there is all these needs around materials innovation, and it takes about 2 decades from the time somebody has a great idea in the lab till you have a material in a product. It takes typically about 2 decades when things work out, right? Many times things don't work out because they're too expensive, not scalable, or that type of thing. So, you know, and then we've got this, well, AI has really done this in other areas, right? Like, you know, you've seen the examples. My examples get staler and staler, right? Every 3 weeks, the quality of the text and images generated by AI gets better and better. So how does this help us solve the very sort of real world concrete problem of materials innovation, right? How do we get materials to market that do stuff that we need with the help of AI? And this means things like, you know, like I said, you know, how do we make lighter alloys for aerospace, right? How do we make energy-dense batteries that can power planes, right? There's a big issue with the energy density needed for planes, right? You know, in a car, you make, you know, electric cars are like a ton heavier than regular cars. Well, that's okay, they're on the road, it's not too bad. But, you know, you cannot make a plane 50% heavier and try to get away with that, right? So there's all these problems. How do we apply AI for that? And a big question is that in digital creativity, and this goes back to the engineering design question, in digital creativity, we're typically okay with tying with an expert. Like that poem, I mean, it was a poem, right? But it's not like Shakespeare, right? It's like, it rhymes, it's kind of quirky, but that's not sort of high literature, right? But we're asking these models to come up with things that we haven't been able to invent ourselves. So the task is actually much harder than the DALL-E or the ChatGPT task of just giving us something, right? Like, imagine this for drug discovery, right? Like this is gonna get put into people. It needs to be healthy. It needs to be safe. It needs to. It's gonna cost like $100 or $200 million to even test it, right? So we cannot just ChatGPT our way to drug discovery, unfortunately. And then there is a lot less data. Same problem, right? There is infinite molecules we could make. There's infinite materials we could make. But we really only have labels for, you know, tens of thousands of them, maybe a million. Like if a data set has 1 million entries in chemistry, that's amazing. That's like incredibly good. I postulate, and a number of people believe, and this takes us to, again, maybe the engineering design question, knowing the explicit rules of the game helps. We're not at a point in chemistry and materials where traditional computer-assisted design is predictive in the way that, you know, fluid dynamics, you know, every car you see has gone through mechanics and dynamics analysis, fluid dynamics in a computer, everything before it's being made. That is trustworthy, it's used all the time. Like Formula One cars, they're not allowed to go into the wind tunnel, so they do CFD in a supercomputer, and they get pretty much the same results, right? Like they cheat. So whoever has the biggest supercomputer gets to do more CFD and outperforms the other teams. Simulations, physics-based simulations in chemistry and materials are quite not there yet. We can simulate, but typically the approximations that we take in order to make things tractable make us pay a price, right? So it's really this continuum in the quality of simulations we can run that very good simulations are unfortunately not applicable to realistic scales and sizes and complexities. So we've got this continuum And over the last sort of 5 to 10 years, AI has become or in general, machine learning has become an integral part of this computer-assisted design in chemistry and materials, right? Where we can use a little bit of AI to boost up our traditional simulations, or we can use our understanding of the physics to make the AI behave in ways that are more data efficient, right? Like we don't need to learn mass conservation from example. We already know mass conservation. It's kind of ridiculous to have to use hundreds of thousands of data points to know that you cannot transmute elements, right? You need to conserve the same elements you had on the left need to be on the right of a reaction. So what are things that are kind of working today? So AI can definitely, if you have sort of 1,000 to 10,000 labels, an AI model can definitely predict what a material would do, as long as it's sort of in the same task as the training data, right? If you have 1,000 alloys, you're in a good place to start innovating in that alloy design space. If you have 1,000 alloys that are metallic and you want to make a plastic, that's not going to work. There's nothing, right? These two domains are so different that they won't transfer. But in domain, we're seeing this every day. So the formulation work that we saw in a couple of talks ago, formulation is, should I mix this with this to achieve these properties? That's a very machine learning problem that works really, really well. So formulating mixtures of something that hits the sweet spot of whatever, viscosity, melting point, that works. And then in protein design, there's been this explosion since AlphaFold. For some reason, I think it felt that proteins was going to be really, really hard. It had been very hard for, I apologize, it's showing you the same image as me. We used to think that, that proteins were going to be really hard, by maybe in the community, because they have been really hard for traditional techniques. But for machine learning, it wasn't that hard. And machine learning models are inventing proteins now that are unseen beyond what nature had imagined. They have really good sort of properties. We're seeing sort of dozens of therapeutic startups around protein design. So we can definitely predict what a material will do. And on the topic of inventing, machine learning models can propose molecules. They can propose proteins. They can propose materials that you would do with things like generative adversarial networks, latent space optimization, or maybe variational autoencoders, diffusion models. The same generative tools that have worked for text and images can, in principle, propose things that you could do. It's like, well, try this polymer, try this alloy. So those tools apply. And like I said, if we have data to score that these are good designs, then we can also say, well, you know, it imagined something, and we can score that is actually good. And more, we can start to have some predictions of how to make the stuff. We go back to the digital to physical question, right? Like, oh, these materials only make sense if somebody makes them. And actually, you know, most chemicals are made by 2, 3, 4 companies in the world, right? These are commodities. They're made at mega scales. You know, there is like 100 million tons of plastic made every year, right? By I don't know, a couple dozen companies. So these things need to be scaled to these very, very, very few players with very, very large capex. So predicting how to make and how to make at cost is very important and a big deal. Not so much for therapeutics. Therapeutics you use very little of, but you want to make textile, like sustainable textiles, you're going to have to make hundreds, you know, maybe hundreds of thousands, maybe millions of tons of whatever you invent. So in molecules, we're starting collectively to use AI for that, starting to work. And then where does sort of LLMs live here? Well, they kind of think, I think. The evidence is that they can co-pilot. You know, it's like having an elder from your institution sit next to you and brainstorm with you, right? It's a little bit like the rubber ducky, a little bit more than a rubber ducky, right? So there's this institutional knowledge that can live in the LLM, but they really cannot be trusted to actually invent, what is a drug that would do this particular, fit this performance metric? Well, it's going to be some reply, and it's going to cost you $200 million to check if that's a good reply or not. So really, the challenge that we're facing is how do we sort of take this, fire hose of digital creativity that seems to be working and translate it into sort of this trickle of market products. And this is typically mediated through humans that need to decide what to make, need to make it, need to put their money where their sort of ChatGPT is and go make stuff. And this is the part that I think is really exciting right now. This is where we're trying to maybe it's, the physics of, well, this is not going to be stable, right? Because, if I put it outside in the sun, it will disintegrate in a day. Well, that's a terrible design. We need to put that somehow in the initial steps of hypothesis generation, right? Or, maybe something like in mechanical, the engineering design we were seeing earlier. Well, of all those bicycles, these two have joints exposed to rain, and they're gonna get rusting like in weeks, right? Well, that's a big deal, right? We need to put that so early in the design that it won't sort of kill us at the end. And again, AI on its own is kind of bad at knowing when it's bad. That's right. It's overfitted to whatever training domain it is. So it's actually really hard for models to tell us this is a terrible idea. We somehow need to find a way to connect existing tools, existing domain knowledge, and sort of these hard constraints. And we'll go back to, I think it was your question about constraints like 20 minutes ago. So there's efforts there. There's been papers about sort of robotized laboratories that not only propose how to make and what to make, but they actually go grab the chemicals. I mean, the person fills in the bottle with the chemicals, but then the robot moves the chemicals around, mixes them, extracts the products, measures whether they're good enough, and runs this in a closed loop to find, in this case, it was optical dyes. This machine can, by the way, make photochromic dyes. It's one of the things they're trying to make in chemical engineering, very close to here. Color purity is always a big deal, but and the one at the bottom was also in Nature at the end of last year. It's the same, but for crystal, it's making solid materials. That one made lots of stuff, but wasn't really good at measuring what it had made. And then the humans went wild when they saw what has come out. It's like, well, you guys, you made stuff, but it's not what you think you did. And again, we go back to this. Humans in science and engineering have been held to this very high performance standard that is much higher again than the POEM standard or the ChatGPT. Yeah, you do this, and if you ask it again, it will change its mind. It's like, oh, I apologize. It's not this, it's that. Well, we cannot do that, with characterization, right? Either something has palladium or it doesn't, right? It cannot be that we have this sort of fuzziness in our tools. So that's where the field is aiming, right? How do we take these tools that are sort of very creative, clearly out of the box, are showing sort of sparks of performance all the way into drug discovery, for instance, and apply them to sort of the rigorous scientific and engineering replies that we need to get materials into the market. And this is my last slide. Thank you very much, folks.